So we started this part. I guess you hear me all right, right? Okay, so we started this part, motivated the problem. We looked at some data, and we realized that in the past, n equals 1 minus 13.6 eV, n equals 2 minus 13.6 divided by 4 eV, and there should be 8 states, all degenerate. However, data says that 8 states split into 2, 2, 4. Well, together is 8. Nonetheless, they are of different energies. But we shouldn't exaggerate the difference because the difference is in this number out of something like 100,000 wave number. Okay, so it is something like one wave number out of 82,000. So it is even like a 0.1% difference. So that's why I said what we learned is 99% more than that accurate. But in order to explain this, there's a long, long story behind it. So the first thing I would like to do today is the simplest effect. We have a hydrogen atom, ignore spin for the moment, and we applied a magnetic field to it. By that we mean this applied field is external. We buy a magnet and apply the magnetic field to the atom. Okay? Later on, we will realize that even if we don't buy a magnet and apply a field, there could be an internal magnetic field, but that is a different story. For the moment, this field is what we applied externally to the atom. In this discussion, remind you one more time, we pretend that spin can be ignored. We don't worry about the spin of the single electron in the hydrogen or all the other atoms, there are multiple electrons in it. That is to say, the remaining effect is the orbital angular momentum of the electron in the hydrogen atom. Okay? Then I would like to remind you how to think about the effect. We have, take hydrogen. We have a nucleus, we have an electron. The electron's motion or the electron state is characterized by a quantum number n, the principal quantum number so-called, and most relevant to our discussion is the quantum number L. Remember the YLM in spherical harmonics, that is that particular L. Just to remind you, L equals 0 is S state, and then L equals 1 is P states. Okay? I said states because L equals 1, Y1, you will have Y11, Y10, Y1 minus 1. You will have 3 P states. Properly linear combine them, you will have what the atomic physicists called PX, PY, and PZ. So I hope that we have a common ground to proceed. All right, we have that. So the most relevant thing to our discussion here is the orbital angular momentum. That is associated with the quantum number L when we go quantum. So how to get the effect in quantum mechanics? We need to find an energy term. to add 2 into the Hamiltonian. Okay? Because this is all quantum mechanics. We have the atomic part, you solved it last term. Now with a magnetic field, we need to add an additional term, what we call the H prime term, the additional term due to the external field. How to proceed? Think classical, then go quantum. Okay? So first point, the orbital angular momentum is accompanied by a magnetic dipole moment. So the orbital effect, because electron is charged, classically you can think about it, the electron is orbiting, thereby it's like a current loop. A current loop will have a magnetic dipole moment. Okay, so let me do it slow motion. Electron orbiting, now this way, it's like a current loop this way. Therefore, there is a magnetic dipole moment. The electron is orbiting this way. The orbital angular momentum is going this way. The magnetic dipole moment is going that way. Okay, they are opposite direction for the reason that by convention, the electron has negative charge. It is our choice of convention. So that's why there's a negative sign. Okay, now if you work out the equation using E and M, the current loop, and then the magnetic dipole moment, so on. Therefore, we will get this ratio. There's a name for it. I think it's called the gyro something ratio. Okay, that has to do with how the angular momentum goes with the magnetic dipole moment for a charged particle. After working things out, the ratio is composed of constants, universal constants, the charge and the mass of electron with a 2, okay? So E divided by 2 mass of electron. It's known anyway. So this is the relationship between orbital angular momentum and orbital magnetic dipole moment. I use a subscript L to make sure that you understand this comes from orbital motion. Okay? Now from this thing, we could multiply a h bar and divide it by h bar, so doing nothing to it. And then we have a very interesting combination of fundamental constants. There are 2 reasons to do that. Reason number 1, we know that in quantum mechanics, this orbital angular momentum has a very natural unit, being h bar, the action. It also has the unit of orbital angular momentum. So if I divide it by h bar, this combination has no unit. Okay, one reason. Another reason, thereby, this is the magnetic dipole moment, and that will carry the unit of the magnetic dipole moment. Okay, so it's worth remembering what this is. E h bar divided by twice mass of electron. This is called the Bohr magneton. All right. So did I write it down here? Okay. This is called the magneton. Here, magneton. Okay. Now, students, CUHK students, okay, you are good in science, you are good in math, you are not so good in English usually. Don't spell it as magnetron. It's not magnetron, it is magneton, all right? Secondly, I will give you the number later. It is very tiny. It is about 10 to the minus 5 eV per Tesla. Okay, now it is a number worth remembering. You will see why. But for the moment, take note of this tiny magneton, Bohr magneton. It characterizes how strong the orbital magnetic dipole moment can be in an atom. Okay. Now, for those who remember what you learned in last term about orbital angular momentum, do you remember that the length of this thing is L times L plus 1 square root h bar, right? That is the orbital angular momentum. Divided by h bar, you wind up with this number. Okay, do you follow me? Do you know what I'm saying? Hello, hello? Okay. Therefore, you plug in 1, you plug in 2, you plug in 3, okay? That is already PDF. It is a boring constant, first of all. It's order 1, right? 1 times 2, square root 2, 1.414, right? Okay, so 2 times 3, square root 6. I think it's 2.4 something like that, okay? And then 3 times 4, square root 12 is 3 point something. So it's nothing, it's order 1. Therefore, what I'm saying is that remembering this Bohr magneton is worth the effort. It is the scale of atomic magnetism. Okay, it's the scale of atomic magnetism, meaning how strong one atom can contribute to the magnetic dipole moment. When you have a solid, you have 10 to the 22 atoms in a centimeter cube. If one atom gives you a few Bohr magneton, then you have a big number that is a magnetic material. Okay, so that is the physics, the sense. Now, we have this, so we can write it in shorthand term, minus Bohr magneton, then this angular momentum divided by h bar. All right. Now, let me do one more thing. I will insert a constant called the G factor. This is G subscript L, meaning it is the G factor for the orbital angular momentum. It is a meaningless one for the moment, but this form will be rather general. A G factor, mu b, and the angular momentum divided by h. Okay, that will give you the magnetic dipole moment. Later on, we will see that the spin angular momentum will give you a spin magnetic dipole moment of the same form, only that this G becomes 2. That is the famous G equals 2 factor in quantum electrodynamics. Second point, now you have a magnetic dipole moment. Classical EM tells us that there will be an interaction energy between magnetic dipole moment and external B field, a dot product, and there is a minus sign here. The meaning of which is that if mu aligns with the external field, the energy will be lower. That is that minus sign. Okay, so alignment is good. The magnetic field tends to align magnetic dipole moment to its direction. So this is classical physics. Now let's go quantum. All we need to do is to give all this quantity a head, being operators. So this looks like a new operator, magnetic dipole moment operator. Not quite. We just said that this mu is proportional to L. So we only need the O operator. Okay, so after we plug in the form for mu, the dipole moment, magnetic dipole moment, we get this energy being mu b constants, the field we applied, and we pick up the Z component of the orbital angular momentum. Why is that? It doesn't matter. We apply a field, we do it, and then we define that direction to be Z. That's completely general, and thereby we pick up the Z component. Okay, so we are done. Here, I give you the value. Okay, you can remember it as 10 to the minus 4 eV per tester or 10 to the minus 5. Okay, 10 to the minus 4 will be more generous, make it slightly bigger so that you can still claim the effect is tiny at the end. The point is, how big a field you can apply in the lab? If you can apply 10 tester, is rather rich lab. Okay, that it already costs you some money to buy that kind of magnet. Now, for high field thing, you need to go to national laboratories that can provide something like several tens of tester. Sometimes you can go to 100 tester, but it's just a short duration, a pulse, so-called, okay? Short duration. With this in mind, you multiply this into this kind of field. See, all goes like this, okay? Now, this is a boring square root 2, square root 3, things like that, okay? So now, with this multiply into this kind of field, we are looking into the energy something like 10 to the minus 3 to 10 to the minus 4 eV. To give you an idea, n equals 2, n equals 3. That difference is about 9 eV. Okay, minus 13.6 minus 13.6 divided by 4. This difference is about 10 eV. Okay, make it rougher. Okay, so we are thinking about 10 eV, and now with an applied field, we may be looking at something like that. The P states here, it splits into 3. What? Okay, see me? That is the big picture, all right? No field, 1s, 2p. These 2p are all degenerate, okay? The difference here is 10 eV. Apply a field, 10 tester, big field already, very rich lab, split. The P state becomes 3, but these differences are of the order of 10 to the minus 4 eV. Okay? If this is 10 eV, I can hardly show you what is 10 to the minus 4 eV. Okay? So that is the big picture. Take this picture with you, then you can explain Zeeman effect. That's it. So let's move on. Take one more look at the perturbation term. This is mu BB setting the scale of the interaction. Then you have the Z component of orbital angular momentum divided by h bar. So no field, we know how to solve the hydrogen atom Hamiltonian. With the field, we found that we need to add a term. Okay? So it is the perfect place to think about what you have in your toolbox. Solve it exactly, turn it into a big matrix and think about it. Variational calculation, perturbation theory, everything goes, okay? Now you have an extra term, okay? Wonderful, okay? Good place to exercise what you learn. So the question is what to do, which tool to use. It turns out that you can try everything, and everything will give you the same answer, because even if you do first order perturbation theory, you get the exact answer. That's nice. The reason is that we can solve this problem, a new problem with an external field, ignoring spin exactly. And exactly without any effort, that's the nice thing. You don't need to do anything more. We can solve this problem exactly. We can do this exactly because of the fact that the hydrogen atom wave function is a simultaneous eigenstate of this H prime. Okay? Now, for those of you who still remember what you learned last term, YLML theta phi is an eigenstate of LZ, and the eigenvalue is ML H bar omega. Okay, I need to ask whether this result is familiar with you. Is that okay? Because the next few pages are meant to remind you of this. If you know this, then it's much easier. Okay? And this thing appears in the hydrogen wave functions. Okay? Therefore, you know the solution to the hydrogen atom. Now, without doing anything, those solutions are also solutions to the new problem with a field. Okay? That is the point. So the next few pages, I remind you of what is orbital angular momentum. This is the definition. These are the operator form, if you like. Okay? And these are the commutation relations. And then, if you write it out in spherical coordinates, this is the magnitude square, and this is the Z component. And thereby, I would like you to know this. Okay? And that will be sufficient for our purpose now. Suddenly, we can solve this problem without any math, further math. Without the B field, we solve this. Okay? We know that there are degenerate states due to the L and ML behind it. Okay? For given L, there are ML states or degenerate. But now, with the B field, we have an extra term in the Hamiltonian. The extra term is related to LZ. Thereby, with the B field, different ML will now take on different energies. The jargon is to say that the magnetic field removes the ML degeneracy. Okay, because the eigenvalue of the whole Hamiltonian will now depend on ML. So this is the big picture. Let's work it out. We have the extra term, okay? And then the atomic wave function has this quantum number ML in it. Now, we just realized that this same set of atomic eigenstate are also eigenstate of this extra term. Okay? We demonstrate it in one line. Hamiltonian has the atomic Hamiltonian O thing with the extra term. We operate this atomic eigenfunctions on both sides, okay? So we, on both terms, so we have this new part. This is the old problem, the atomic problem that in general should give us energy depend on N and L. Only for hydrogen, we have an accidental degeneracy that E depends on N only. For general spherically symmetrical potentials, central force problems, the energy should depend on N and L. For example, 2P, that is 2, 1, okay? But now, with the magnetic field interacting with the magnetic dipole moment due to orbital angular momentum, we have this part, and this LZ on the atomic wave function will give us MLH bar. So these are eigenstate. And this H bar cancel with what we just did. We want to make this a number, right? So we have this ML mu BB, okay? As I told you, mu BB set the scale 10 to the minus 4 eV or so, or 10 to the minus 3 if you have a big magnet. And ML is 10 minus 1 for P state, 210 minus 1 minus 2 for D state. It's a boring integer, 0, 1, 2, that's it, okay? Even for F state, okay, it is 3, 3, 2, 1, 0, minus 1, minus 2, minus 3 is up to 3. So it's still 10 to the minus 3, 10 to the minus 4 UV. You see, after doing that, we have solved the problem exactly. Okay? Now, for those who like perturbation theory, you may want to do first order perturbation on it, right? By that, you mean you take the 0th order state, work out the expectation value. So we work it up to here. You left multiply the same state, do the integration that will be normalized. Thereby, you pick up this extra term in the energy. Even you apply first order perturbation. That's fine. Even if you don't realize that it is exactly solvable, you apply first order, you get the exact result because it's the same procedure, okay? Or else you can say that first order perturbation already is exact. In the big matrix problem, it means all you have after writing it out is the diagonal elements. All the off diagonal elements are 0 exactly, even if you work out the elements. Okay, and that is easy to see because it's a number times this thing. If you multiply into multiply into it a different atomic state and do the integration, that will be 0. Okay, so all the paths, all the tools converge into the same answer because it is exactly solvable without effort. So let's get the physical sense of the problem. Okay, now This example is a D state, L equals 2. If you don't have B field, the energy would have at least 5 flow degenerates because ML is 2, 1, 0, minus 1, minus 2. For example, this is 3D, N equals 2, okay, N equals 3, L equals 2 is 3D state. You will have all these 5D states degenerate. You turn on a field, becomes something like that, okay? According to the ML value, the energy will be lined up from higher to lower. Nonetheless, the pattern is very nice because they are evenly spaced by this mu BB that sets the scale. And that cannot be big. It's about that, okay? For P state, ML is 1, 0, minus 1, thereby it is like this. See my fingers, okay? So this will give us the change in the atomic state's energies. Now it's time to introduce the Zeeman effect. What do we mean by Zeeman effect in general, this term? This term in general means spectral line, spectrum. You have a spectral line somewhere in a frequency, okay? A Lyman line, for example, a Balmer series line. When you apply a magnetic field, Zeeman, back in the end of 19th century, observed that sometimes a line split into several lines. For example, 1 line into 3 lines. But if you observe the spectrum carefully, you also see sometimes 1 line goes into 4 lines. 1 line goes into 6 lines, okay? Nonetheless, Zeeman effect, umbrella form, in an umbrella sense, refer to splitting of one spectral lines into several spectral lines in the presence of an external B field. So that defines the Zeeman effect. I already explained this, okay? So now let's look at the effect. Spectral line has to do with transition between possible energy states of an atom. This change from a higher state to a lower state, the energy will be given out as a photon. Therefore, you use a detector to observe that light, you get a spectral line. Another way is absorption spectrum. You shine in a wide spectrum of a wavelength or frequency, and an atom will selectively absorb some of the right energy thing, and then at the end, you detect what is missing, you get the absorption spectrum. So you have emission spectrum, you have absorption spectrum, but both will give you the same information. Okay? Understand? Now, after we understand that applying a B field, okay, the state will split, remove the ML degeneracy. Now we have a way to understand Zeeman effect. For example, 2p, 1s, okay? 1s, 2p. You understand what I'm saying? Okay? Some of you may wonder, why didn't I discuss 1s, 2s? Okay? Now, later on in the course, we will see that 1s, 2s, because it's s and s up there. And when I shine in the light, there is something involved about the atom that is called the interaction. Okay, that has to do with the electric dipole. When you involve 1s, 2s, and the electric dipole moment of the atom, that integration turns out to be 0. In the past, some of you may have heard something called the selection rule, and that is the selection rule. So we don't discuss 1s, 2s transition for the moment, because that is called not allowed. The allowed ones are 1s, 2p. And p means L equals 1, thereby ML is 1, 0, minus 1. Okay, do you follow me? 明白唔明白? Okay. And then, if I don't have a magnetic field, there will be one transition energy because they are degenerate. Okay. With a magnetic field, they split, thereby these 3 states could have transitioned to the 1s, and we will see 1 line goes into 3 lines. Okay, do you understand? That is the basic idea of the Zeeman effect. Okay, now we have solved it quantum mechanically, and exactly, because it's easy to solve. We don't need perturbation, okay? That is the point. Now, I would like you to accept a result so that we can move on. I mentioned selection rule. The one I mentioned is about L, okay? It's delta L equals plus minus 1. So 2p, p to s, L equal 1 to L equal s. There's another selection rule about ML. The delta ML is 0 or plus minus 1. Later on in the course, we will discuss time-dependent perturbation theory in the module regarding light interacting with matter, light interacting with atom. What to do? It is time-dependent because light is oscillating E field or F oscillating B field. So you have cosine omega t. All the perturbation term we discussed so far has no time in it. That's why we call time-independent, degenerate or non-degenerate perturbation theory. Okay? So for the moment, I claim this selection rule on ML. Thereby, you exercise this selection rule, we will have 1 line goes into 3 lines. This is called the normal Zeeman effect. Okay? By normal, we mean it is the simplest mechanism. Okay? Now, let's see. Okay. What happened if we consider 3D goes to 2P? So here I depict a 3D and a 2P, for example. Okay. We discussed D state. There are 5 degenerate states. Magnetic field will lift or remove this degeneracy. And then we have 5 different D states energies. The same, this interval between neighboring splitted states is mu BB. Okay? And now for the P states, we have 3 degenerate states now split. And then we have this mu BB. Okay? Now, we need to exercise the selection rule of delta ML. When we do that, we can map out all the possible transitions. For example, from 2, it can go to 1 only. That is the only possible one. If you go from +2 to 0, delta ML is 2. It does not follow the selection rule. However, if you start from 0 up here, okay, now you can go to 0 down here. Which one? This one, okay. From 0 goes to 0 is allowed. From the same state 0 here, you can go to -1, that is allowed, different by -1. And then if you start from 0 here, you go to +1, is still okay. All right, so for this state, there are 3 transitions. So it looks like there should be more lines, right? No, you have to work out the difference in energy. Here, intentionally, the figure group these transitions, they all different by this kind of energy, okay? And at the end, from the line that appear without field, even there are 9 transitions, there are only 3 energies. So you have recovered the same energy, the same line without a field. Even in the presence of field, there consists of 3 transitions. They all occur at the same h bar omega. And then there's a line higher energy, a line at lower energy. 3 lines. Okay, that is the normal Zeeman effect. So Zeeman, Dutch physicist, received the 2nd Nobel Prize, so much earlier than quantum mechanics was established. So far, our conclusion is that no field, no B field, 1 spectral line. With field, the effect should be 3 tiny separation lines. Okay, this is 10 to the -4 eV scale. This is what Zeeman observed in some atoms. So let me show you the phenomena. So far, we discussed the normal Zeeman effect. This is this phenomena. Well, I must tell you that the normal Zeeman effect is not something normally observed. It is observed in only a few atoms. For example, helium. It does show this normal Zeeman effect, meaning 1 line split into 3 lines. However, most atoms do not show this specific 1 goes into 3 line phenomena. Instead, the spectral lines do split, but it's split into a different number of lines. Here I show you several examples. 1 could go into 6 lines. 1 could go into 4 lines. Okay, sometimes it go into 10 lines. Even number, not 3. Okay, so we ought to give another name to this Zeeman effect, splitting into even number of lines. They are collectively called enormous 異常的, 异常的, enormous Zeeman effect. We have to ask then, hey, we did quite well. We solved this additional effect exactly, assuming the only effect comes from the orbital angular momentum. So what's wrong? The answer is obvious. We ignore the spin so far. So maybe when we include spin orbital and spin angular momentum into consideration, accompanying that is a spin magnetic dipole moment. When we include that into our whole consideration, we may be able to explain why one spectral line will split into even number, not 3 spectral lines. And that is indeed the correct path to pursue further, okay? That leads us to our summary. First of all, the prediction is 1 line goes to 3 line, ignoring spin, only orbital angular momentum effect. Then we may ask, when could we ignore spin so that this effect works? You can stretch your imagination a little bit. For example, if we have 2 electrons, helium, those electrons, as you know, in elementary chemistry course, is you always write it as one is up in 1s and other is down in 1s. Thereby, vaguely, you have this idea that their spin tends to cancel each other. But a warning, this picture, this sentence, you can hardly rate it as right or wrong because it's so vague. One up, one down. What we meant by that? What is the spin wave function? Okay, then we have to learn a little bit more about angular momenta in quantum mechanics. Nonetheless, that is the sense. In such cases, that spin may be cancelled. Therefore, we are legal to ignore spin effect, and therefore this normal Zeeman effect comes out for observation. But other than that, if we have hydrogen, we only have a single electron, we better be careful about the spin effect. We shouldn't ignore it. Okay? So what's next? We are done with the normal Zeeman effect. It is observed in some, but not in many atoms. Then what's next? We still have this fine structure that we want to explain. Then we have the enormous Zeeman effect is still a puzzle to us. Seems to be the case that we ought to include spin into our consideration. And that is the next section. So let's take a break for a few minutes, and then we will resume, and then we will discuss generally angular momentum in quantum mechanics, because spin is one of them, orbital is one of them. Later on, we need to add them into a total, and total angular momentum is also an angular momentum in the quantum mechanical sense. So it's better to have a big picture of what angular momentum in quantum mechanics behaves. So break now.